Welcome back, and we're going to continue our review of chemistry with a real short clip on isotopes. And so what we've got to remember about isotopes is they're versions of the same element with a different number of neutrons. And so the two most common ones that you've probably heard of are carbon-12 and carbon-14. So if you think back to earth science, you may have done some stuff with half-lives and radioactive dating where you talked about how carbon-14 is radioactive and it decays. Well, the difference between them, if we look at the carbon-12, it has 6 protons. It also has 6 neutrons, and so it has an atomic mass of 12, 6 plus 6. Well, carbon-14 still has 6 protons. That's what makes it carbon, but in this case it has 8 neutrons, and so it has an atomic mass of 14. Now, when you look at the periodic table and you look up the atomic mass, you won't see 12 or 14. You'll see 12.011. Well, we can't have part of a neutron. We can't have part of a proton. So where does it come from? Well, the atomic mass is the average of all the isotopes. So in the case of carbon, we have carbon-12, which accounts for about 99.9% of all carbon, so most of it. And we have carbon-14, which is less than 0.1% of the carbon that's out there. So if we take the atomic mass times the relative proportion, in the case of carbon-12, that gives us 11.988. And in the case of carbon-14 times 0.001, we get 0.014. And so we get 12.002, which, although not exactly what comes off the periodic table, the proportion's a little bit off. That's where the atomic mass comes from. It's the average of all the isotopes that are out there. So let's do an actual example here with strontium. So strontium has 4 naturally occurring isotopes. There's strontium-84, 86, 87, and 88. And here's the relative proportions of each of those. 84 is 0.5%, 86 is just under 10% at 9.9, 87 is 7%, and 88 makes up the bulk of it at 82.6. So all we're going to do in this case is we're going to take the atomic mass of the isotope times the relative proportion. So in this case, we're going to go 84 times 0.005, and that gives us 0.42. In the case of the 86 times 0.099, and we get 8.514. And the isotope that has the mass of 87.07. So we're using the decimal equivalent of the percentages, and that gives us 6.09. And finally, the most common isotope with the atomic mass of 88, we're going to multiply this by 0.826. And for that one, we get 72.688. If we add all 4 of those isotopes together, we get 87.7, which is the atomic mass given on the periodic table. So the atomic mass given on the periodic table is the average of all the isotopes that are naturally occurring. So now when it does decay, so when carbon 14 decays, it becomes nitrogen 14. Where does the particles go? So I'm just going to go real quickly over that. The first kind of decay we have is called alpha decay. And here's the case of when uranium, which we know to be radioactive, decays into thorium. And what's given off here is an alpha particle. And each alpha particle has 2 protons and 2 neutrons. So when it leaves, the atomic number is reduced by 2, in this case 92 to 90. The atomic mass is reduced by 4, in this case 238 to 234. So there's an alpha particle. The next type of decay is beta decay. We're only going to look at beta minus decay. There's a beta plus decay. But in beta decay, what happens is basically a neutron, it splits into a proton and an electron. So the radiation given off is an electron, and one of the neutrons is converted to a proton. So in the case of carbon-14, it actually turns into nitrogen-14. So if you look at the blue dots here on the left, we've got 1, 2, 3, 4, 5, 6, 7, 8. There's 8 neutrons. After beta decay, we've got 1, 2, 3, 4, 5, 6. 7. There's only 7 neutrons. And we have one additional proton, which turns it into nitrogen, and the radiation given off is in the form of an electron. And finally, gamma decay is basically when an excited photon is given off. It doesn't change the element, it doesn't change the atomic number, it doesn't change the atomic mass, but the radiation given off in this case is a photon. So if we look at those in terms of the penetrating distances, alpha particles are stopped by paper. They are not very powerful to come through. Beta will make it through paper and is stopped by plastic. Gamma rays, on the other hand, they can make it all the way through, and they are stopped by lead. So that's when, if you go into the doctor's office or dentist's office for an x-ray, they'll put the lead apron in front of you to prevent gamma radiation from reaching you. And that's the end of our quick isotopes unit, and you can use this information to find the atomic masses on the homework.